Welcome back to this explainer. Okay, so if you're gearing up for your discrete math midterm right now, you are in exactly the right place. Consider me your enthusiastic professor for the day, because we are doing a fast, high-yield review of Chapter 1. We're going to lock down those foundational concepts of set theory that, trust me, show up on the exam every single semester. So, here's our game plan for today's review. We're going to hit 1. Foundations of set theory. 2. Roster versus set builder notation. 3. The empty set pitfall. 4. Finite sets and cardinality. 5. Sets in computer science, and we'll wrap it all up with 6. Set equality practice. All right, Section 1, Foundations of Set Theory. Let's just dive right into it. Now, we really can't master the midterm without absolutely solidifying the very first definition in the textbook. A set is essentially a way to formalize the idea of grouping objects together so we can view them as a single entity. The objects inside, those are your elements or members. But the absolutely crucial word you need to remember here is unordered. A set is an unordered collection. I want you to keep that explicitly in your mind because it's a vital detail that's going to come back to test us in our final practice problem. Moving right along to Section 2, Roster versus Set Builder Notation. Knowing what a set is won't help much if you can't read the math, right? So let's look at the two main ways you're going to see these collections written out. First up, we have roster notation, which is sometimes called the tabular form. This is super straightforward. You literally just list out every single member separated by commas inside a pair of braces. Like set A here, which is exactly A, E, I, O, U. But then take a look at set builder notation. Instead of listing out all the elements, it just states the rules or properties that define the members. So set B reads as the set of all x such that x is an even integer and x is greater than 0. For the exam, you need to be completely comfortable seamlessly translating between both of these formats. Okay, Section 3, the empty set pitfall. Honestly, lean in and pay close attention here. This is the most notorious trap in discrete math. It's the exact place where students lose points every single semester without fail. So let me ask you this. Is the empty set symbol, by itself, the exact same thing as the empty set symbol inside a pair of braces? Just take a second and commit to an answer in your head. Well, if you guessed they're the same, you just fell right into the trap. But hey, don't worry, that's exactly why we're doing this review. The computer folder analogy clears this up instantly. The symbol on its own, that is the empty set. Think of it as a completely empty folder sitting on your computer desktop. But when you put braces around it, it becomes what we call a singleton set. You can think of that as a folder that contains exactly one thing inside of it, which just happens to be an empty folder. So the massive takeaway here is that the singleton set actually has one more element than the empty set itself. It contains one item. The empty set contains 0. Make sense? Next up on the syllabus, Section 4, Finite Sets and Cardinality. Speaking of counting elements inside a set, I'm just putting this number up here for a reason. 26. Think about it for a second. What super common set has exactly 26 distinct elements? Yeah, it's the set of letters in the English alphabet. And that brings us perfectly to the formal definition. If a set has a finite number of distinct elements, let's just call that number n, then n is the cardinality of the set. You're going to see it written on your exam as either the set name inside absolute value bars, like A, or as n of A. So jumping back to our previous example, if S is the set of the English alphabet, the cardinality of S is 26. All right, Section 5, Sets in Computer Science. Now, I know some of you are computer science majors sitting there asking that classic question, why do I even need to learn abstract math? Well, let me connect this directly to your future careers. Every single time you write code, you use data types, right? But what actually is a data type fundamentally? A data type in computer science is built entirely upon the mathematical concept of a set. It's literally just the name of a specific set bundled together with the operations you're allowed to perform on the elements of that set. Check this out. It brilliantly illustrates the connection. Take the Boolean data type, which, runs the logic of our entire digital world. It is quite literally just the set containing the elements 0 and 1. That's the whole shebang. And it's paired with operations you can perform on those elements, like and, or, and not. You aren't just learning abstract math today, you're literally learning the architectural blueprint of computing itself. Okay, let's wrap this up with Section 6, Set Equality Practice. It is time to put your newly reviewed knowledge to the test. Let's tackle a problem straight from the exam review sheet. This is solved problem 1.1. Take a really close look at these four sets. Set A has elements R, T, S. Set B has S, T, R, S. Set C has T, S, T, R. And set D has S, R, S, T. So which of these sets are mathematically equal to each other? Remember, think back to the very first definition we covered today. And the answer is they are all exactly the same. If you got this right, fantastic job. Remember what we said, a set is an unordered collection. The order in which the letters are listed means absolutely nothing. And on top of that, listing an element multiple times inside the same set doesn't change the set at all. Repetition is totally ignored. Sets A, B, C, and D all uniquely contain just three distinct elements, R, S, and T. So we've covered a ton of ground today, from avoiding the empty set pitfall to calculating finite cardinality, and even seeing how our data types rely on this exact logic. But before you close your notebook, I want to leave you with this final, kind of provocative thought. We know that basic operations on the tiny, finite Boolean set run all the incredibly complex computers on Earth. As we move into Chapter 6 and start exploring infinite sets, I want you to wonder what kinds of infinite sets and complex operations are required to run the universe itself. Good luck on that midterm, stay curious, and I'll see you in the next explainer.